All right, welcome to lecture number 9 of the course Design of Machine Elements and Systems in Agricultural and Biosystems Engineering. The topic is on load stress analysis, and after a very extensive discussion on the materials, okay, the selection of materials and their uh, properties, okay, we now proceed with a review of stresses, okay. And this is just a fundamental discussion, okay, because the compressive and tensile stresses and also the shear stresses and other uh, stresses have been previously discussed. Now, we proceed with the discussion of the specific stresses of concern in machine design. And primarily, there is normal stress, or the stress resulting from forces applied perpendicular to an area, okay, an area of design. Now, there are two types of uh, normal stresses, and which shall be discussed later, okay. And we have also shear stress, and this results from forces, okay, that are parallel to the plane area, as can be seen, okay. Now, again, okay, there are two types of stresses, okay, and these are, okay, compressive and tensile stress. And while they have similar similar formula that can be used, okay, to determine their values with respect to a certain area of a material under stress, okay. The difference is in the notation, okay, to denote, okay, compressive stress, there is the force of compression, Fc, and if it's tensile, then it's Ft, F sub T, okay. And it's with respect, okay, to the direction of the force with respect to the area. So you have a compressive, okay, going towards the area of concern, while in tensile, it's pulling, okay, from the area. Okay. Now in shear stress, okay, there's only one formula, and it's F over A. Okay, I'm giving you the shear stress, okay, in equation number 2. Now again, the area of concern is shown, okay, and if it's the same size as that of the normal stress, then you have the same area, okay. Now, due to forces applied to bodies, okay, there is what is called strain, and this is the result, okay, of the stresses, okay, when a certain body is being pulled or being pushed or being slid again past each a certain area. Now, in normal stresses, the resulting strain is called normal strain, and it's simply the change in length per unit length. So it's the change, okay, it's a delta variable with respect to the length. And so it is what? It's in the same direction, okay, as the applied stress. In shear strain, okay, it's the change in the angle formed between two planes that are orthogonal to prior to the deformation, okay. As can be seen on the diagram, okay, the degree, okay, the degree of the angle, okay, is visible via the original orthogonal, okay, the orthogonal position, okay, and then against the new, okay, the angular deformation, okay. Now, the normal stress okay, and well, the shear and normal stresses of materials can be related to the strain, and it would depend on the material, basically because of the structural components, okay, the formation, and also, well, the inherent properties of that material. Various materials have different behaviors and relationships of this stress strain. Okay, now the stress strain relationship is modeled using this stress strain diagram in figure number 1, and it's important to take note, okay, okay of specific uh, portions of this diagrams, and you have here, for example, the plastic strain, okay, the elastic strain, okay, and this, okay, this are specific points related, okay, to the behavior of the material when they are experiencing stress. Now, elastic strain is, okay, is the strain resulting from stress that allows the material to recover when it's unloaded by the stress, with the force, okay, and well, the stress eventually. On the other hand, you have plastic strain resulting, okay, from um, from the stress, okay, wherein the material could no longer recover from um, the deformation it has undergone, okay, because of the loading, okay, and even after unloading the force, okay, or the stress. Now, the plastic strain, okay, um, it happens after this certain portion in the diagram, which is this yield strength, okay, and why? Because this the properties, okay, the change in the strain with respect to your stress, okay, 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 the stress, okay, the stress with respect to strain is it's beyond, okay, beyond control already. So it the material, uh, due to its properties, okay, it could no longer revert back to its original position. Okay. This is the portion, okay, up to this point. You have the okay, you have the sorry, wait, I have to change the color. Sorry, what's happened? Okay, let me go back. Okay, discussion. Okay, so you have the degree of plasticity as the ratio, okay, of the plastic strain to the total strain when a material is loaded to a certain load and unloaded. And elasticity on the other hand is the ratio of the elastic strain to the total strain. And you have here the Young's modulus, okay, and it's denoted by letter E, which is actually the uh, stress, okay, over your strain, and it's linear, okay. The Young's modulus is linear, so that, okay, so that after the yield strength, the material which now behaves in the plastic um, behavior, okay, will be unpredictable, okay, and then there's an ultimate strength, and afterwards there's fracture. Now, materials, okay, are tested using the universal testing machines, okay, to determine this certain diagrams. Okay, depends on the material. If it's steel, how much carbon is in the steel, it differs. Okay, now there are also, okay, relationships with respect to your shear strain. Okay, that's the modulus of rigidity G, and there's the bulk modulus, okay, describing the response of a solid to dilatational stresses. Now, the direction of this discussion is to take into consideration, okay, the normal and shear strain of that materials are experiencing during the operation of a certain machine. Okay. Now, it is important that this be considered. Okay. And we now introduce here the Poissons ratio, which is simply the change, okay, in um, the or the deformation in terms of the diameter over the deformation in terms of the length. Why? Okay, because, okay, take note that a material, okay, when it's stretched, it eventually, okay, loses its uh, dimensional properties along the the diameter. Okay, so please see the figure. Okay, originally you have a material that's experiencing normal uh, stress, okay, with the force F along its area A, and it deforms along two dimensions, along the length and along the diameter, so that there's a change in the diameter. So you have now a delta D prime, and the length becomes L prime. And the Poissons ratio, okay, is, okay, covers, or it represents this change in the diameter and the length. It's given by the formula in equation number 3, mu, okay, equals the quantity delta D over D all over the quantity delta L over over L. Okay. And where does this go? Okay. After discussing materials, okay, and the stress and the strain in relation to the materials, okay, it is important to take note, okay, of the factor of safety, or the safety factor, or FS. Okay, and this factor of safety is important in as a buffer or a margin to cover for uncertainty in the operation of the or not just the operation, but all uncertainties during the life of a certain machine. Okay, because, okay, once an engineer has computed for the theoretical design, okay, for the machine, okay, there are still unknowns that the engineer might, or the material or the machine would be experiencing along its development. There could be problems in, well, the fabrication, okay, and the manufacturing, okay, errors in the fabrication and manufacturing of certain pieces of material of the machine. There could be what? There could be also certain unknowns, like in the material properties, okay? So it's part in the machine design. And eventually, there's the eventual wear and tear of materials. So there's use, okay? Now, the factor of safety is simply the strength over the maximum allowable stress. And there's not much of a problem in considering the factor of safety, simply because there are known, okay, there are identified standards to use, okay, or the numbers to use in as the factor of safety of during development or design of a machine. And these are, okay, based on the applications of the machine, okay, particularly the material properties and the environmental conditions. In terms of the material conditions, the environmental conditions, there's the use, there's the stresses and the loads applied, and also uncertainties, okay, with respect to the use and environment. Now, as can be shown, okay, there's an F is used for material properties that are known, and it's 1.25 to 1.5. It goes down to 3 to 4 when the materials are untried, okay, and the environment is uncertain. Okay. Now, the fatigue strength, vibration resistance, and impact forces should be considered beyond the strength of the material as well. Okay. Now, it is important to take note that in dealing with stresses, okay, the based on the discussion of the Poisson, okay, the stress, okay, the stress of a material, okay, relates between the shear and the normal stresses. Now, the Mohr circle, okay, it's a technique that's used, okay, to determine, okay, combined loadings. But in this particular discussion, there's stress, or there's a stress on the stress transformations. And what does it mean? Okay, for a material as shown, okay, this is a 3D infinitesimally small material portion of a certain body or a certain material. Okay, and that material is experiencing normal stresses and also shear stresses, as can be seen. Okay, now this can be, okay, handled at the same time. So, and how? Okay, and this can be simplified further by, okay, by looking at just a 2D representation. But anyway, in this drawing, okay, in this drawing, okay, in this drawing, the material is experiencing what? It's experiencing normal stress along the Y, along the X, along the Z. Okay, so 3D. Okay, now there's also shear stress along, okay, along the Y, okay, along the Y surface, along the X surface, and along the Z surface, and it depends on the direction of the shear stress. Okay, and how do we, okay, take into consideration? Okay, we can transform this, okay, these forces, these stresses that the body is experiencing. Okay, and we'll show you an example. But before we do that, let's analyze a 2D equivalent of this drawing. All right, so we now have a 2D, simplified 2D representation of the 3D drawing we were talking a while ago. And we have the forces, okay, or stresses along the X, along the Y, and then I mean, those are normal stresses, and then there are the shear all around the surfaces, or the line, okay, the lines, okay, of the X and the Y dimensions. Now, with stress transformations, okay, if we take a different look of the infinitesimally small portion, okay, and we rotate it to a certain degree, okay. Originally, there's the X and Y, okay. The X and Y are over along these directions, okay, the X and the Y, and we have a new, okay, orientation all along this one, okay, to take into consideration during computation of the stresses. And for example, that is denoted as delta. Sorry, theta. Okay, it's theta. And we have, okay, Y prime over here and X prime over here. Now, the solution to this one, okay, when we say stress transformations, okay, we transform the original stresses along the new directions, okay, the y prime and the x prime. So this has been already discussed in the previous subject of stress of materials or materials of engineering. Yes, materials of engineering. Sorry, mechanics of materials. So we have the transformed, okay, normal stress along the x prime as, okay, with respect to theta, okay, because we are using theta. So it's the original x times cosine squared theta plus the y, okay, the y times sine squared theta plus 2 times the shear, okay, the original one times sine theta cosine theta, okay. That is now the transformation, okay. And you have your shear along the x prime y prime with respect to theta, and it's going to be minus, okay, the original sigma x, okay, the original normal stress along x minus the original normal stress along y times sine cosine theta, sorry, sine theta cosine theta plus the shear along xy, okay, times cosine squared theta minus sine squared theta, and you have your y prime, okay, with respect to theta. If you look at the along the x prime, okay, it's somehow similar looking to that one, so it's as shown. Okay, it's going to be minus 2, okay, the shear cosine theta. Now, given, okay, that cosine, okay, squared theta is equal to 1 plus cosine 2 theta over 2, and you have also sine squared theta equals 1 minus cosine 2 theta over 2, okay, and also that sine theta cosine theta is equal to 1/2 sine squared theta. Okay, these are trigonometric properties which can be used now to simplify this formula, and we get, okay, the following. Okay, it's going to be sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cosine 2 theta plus, okay, the shear sine 2 theta. Conversely, okay, you have your y, your sigma y prime, which is, okay, it's sigma x plus sigma y over 2 minus sigma x, okay, that quantity. Minus the shear. And you have finally your shear okay, it's minus, okay, sine 2 theta plus shear cosine 2 theta. And what are the implications of this one? Okay, these are actually used, okay, they're used, okay, to compute for the more critical stresses called the principal stresses, or the maximum in plane shear stress. Okay, based on this numbers or this formulae, okay, this principal stresses, okay, and the maximum in-plane shear stress, okay, can be determined, okay, particularly if a certain material is experiencing shear and normal stresses combined, okay, or combined. These are combined stresses, and this is what happens, okay, when machines are being used or are in operation. This the material, okay, will be experiencing both normal and shear stresses, and we'll see in a while, okay. But okay, to to show, okay, let's move over to the next slide, okay. And this is just to summarize, okay, based on the relationships as shown a while ago, the principal and the maximum in-plane shear stress that stresses, and other related parameters, okay, such as the angle or of normal vector, okay, and the principal stresses, okay, in relation to your into the normal stress, okay, this is bigger and much more, or it's higher compared to that normal stress, okay, because there's a combination of the shear stress and the normal stress in a certain direction, okay. This can be explained later in the next lecture, but let us proceed, okay, to this a sample computation involving this principal and maximum in-plane shear stresses, okay. And it would not be better without if not for an example in machine design, okay. So you have here a propeller, okay, this is used as an aerator, okay, and this is in an agricultural engineering discipline, okay. So a water aerator with a propeller, okay, that propeller is experiencing a drag force of 120 kilonewtons, and the drive shaft, okay, is transmitting 2,500 kilowatts of power to this propeller, okay, at 100 RPM. Now the shaft radius is 100 millimeters, so it's directed to the propeller, okay, and it's rotating. Now what's being asked, okay, are the stresses on the surface element oriented with the axis or the axis of the shaft, okay, and the principal and maximum in-plane shear stresses. Now, how to proceed with this problem, okay? This is very much a direct example of what was being discussed a while ago on the principal stresses. And let's proceed with the solution. So we're back in this whiteboard, okay, so that we can solve for the problem. Now we have here, okay, we have here a shaft, okay, the propeller, and the propeller, okay, is experiencing what you have here, the shaft, okay. Let's just simplify it as that. Let's no longer draw the propeller, but just the shaft, okay. So you have a shaft that is experiencing a certain drag force that is equivalent to 120 kilonewtons, okay, along this direction as well. And then there's what? It's rotating, as was said. So it's rotating at a certain RPM, and you have it's 1,000 RPM, and simply there's going to be a torque. Okay, we will still have to determine that. But what's being asked, okay, are what? Letter A. Okay, so you have the given. There's power, okay. The power is what? The power is so it's 1,000, and you also have the power. Okay, this is the RPM. The power is 2,500. It's what? It's kilowatts. Okay, kilowatts. Okay, kilowatts. Very big one. All right. I'm not sure how big the aerator is, but anyway, it's very big, kilowatts. So you have you're trying to understand, okay? You're trying to find um, the principal and maximum in plane shear stress, okay? And also, okay, we are trying to find, okay, the the stress, okay, in the surface, okay. So you have here, okay, the torque. The torque is equal to what? Okay, the torque is equal to power over uh, okay, W. Okay, okay. This is the angular. Okay, the angular velocity. So you have your power, okay, directly available. It's 2,500 kilowatts. What about the angular velocity? So your angular velocity W, okay, is what? It's RPM. Okay, so let's go directly 1,000 revolutions per minute. Okay, times convert that, okay, to rad. Okay, and one revolution is 2 pi rad. Let's convert the minute so that we get rad per second. And solving, okay, this would yield 104.7 rad per second. Now, how about the torque? Okay, so we can solve now for the torque, which is just what? This is 2,500 times 10 to the 3 Newton meter per second divided by 104.7 rad per second, and give us the torque, okay, of 23.9 kilonewton meter. Okay, that's going to be the force in the surface. Okay, now torque is going to give, okay, it's going to be causing a shear stress along the um, the direction of the surface of, or along the surface of that um, shaft. Okay, so we now find the stresses. Okay, define the stresses, and the normal stress is going to be what? It's going to be F over A. It's going to be compressive. Okay, so it's going to be negative 120. Okay, kilonewtons times 10 to the 3 newtons all over the area. And what's the area? The area is given a radius, okay? So it's pi r squared, going to be pi times 0.1. It's 100 millimeters. So 0.1 meters, okay? It's going to be 0.0343142 meters squared. So your normal stress is now 0.03142 meters squared, and it's going to be negative 3.820 megapascals. The direction, okay, the design, okay, it's the sign, the negative sign is just indicative of the direction of this stress. Okay, how about the shear stress? Okay, the shear stress is going to be caused by the torsional, okay, the torque. So it's going to be TR over J. And what's J? Okay, it's the okay, moment of inertia. Okay, you have your so we have now the torque 23.9 kilonewtons, okay, times 10 to the 3 Newton meter. and you multiply it by the radius of 0.1 meters. The J is going to be, okay, it's going to be pi times the r to the fourth over 2, which is just pi times 0.1 meters to the fourth over 2. Okay, so it's going to give or yield 0.1571 times 10 to the negative 3 m to the fourth. So the shear is going to be okay, so the torque times the radius divided by the J will yield 15.22 megapascals. This is not done. So there's a continuation, and what's being asked is the principal stress. Okay, now the principal stress is a combination of both the effects of this the shear, okay, and the normal, and it actually becomes bigger. And to find that, okay, to find the principal stresses, okay, because there are two, okay, and it would depend which one is bigger, because eventually one would become a tensile tensile effect, while the other is still compressive. So let's make use of the formulae given. So the formula for the principal stresses is actually I've shown is sigma x, okay, plus over y, 2 plus or minus, okay, y two values because there's a plus or a minus, okay, one would yield another number, okay. All right, so this will become, okay, negative 3.82 times 10 to the sixth. This is to the sixth, okay, to the sixth megapascals. Oh no, sorry, it's already mega. So pascals, okay, but y is 0, okay. So this is going to be divided by 2 plus or minus, okay. So y is the y portion is 0. Okay, so negative 3. So same as the 1. So we have negative 3.82 times 10 to the sixth Pascal plus 0 all over 2, and we're going to square that. Okay, plus the shear stress 22 times 10 to the sixth Pascal squared, and this would yield, okay, negative 1.91 times 10 to the sixth Pascal plus or minus, okay, 15.339 times 10 to the sixth Pascal, okay, and if you simply add this, okay, your well, the sigma 1 is going to be 13.43 megapascals, while the second principal stress is 17, but negative, okay, so it's compressive, 17.25 megapascals. So this is the first solution to that. Okay, later when discussing the Mohr circle, okay, this will be further explained. Okay, now for the maximum, okay, the maximum, okay, we're trying to find the maximum in plane shear stress, and it's simply what your max. Okay, the shear max, the shear max is going to be based on the formula. Okay, sigma x plus sigma y, okay, all over 2 squared plus the shear, okay, computed shear, and it's simply going to yield, okay, it's going to yield 3.82 times 10 to the 6th Pascal plus 0, and you have divided by 2 plus the shear, which is 15.22. You then get, okay, solving for this one, we get maximum shear as 15.34 megapascals. Now, as to the directions, okay, the directions for your, so this is directed, okay, if you're going to solve for the angle, okay, the delta data is going to be 1/2 tangent negative, or the inverse tangent of 2 times what, the shear, okay, the shear 15.22, okay, times 10 to the 6th pascals, 4 over negative 3.82 times 10 to the 6th Pascal, and this will result to what? Okay, okay, it's going to become negative 41.42 degrees, or 138.6 degrees. Again, the direction is just indicated by the negative sign. So this is the second. Well, the first will have a, okay, so it's going to be 48.58 degrees. Now for the shear, okay, the shear is going to be in a direction, okay, that is, okay, sorry, theta s is equal to 1/2 tangent, okay, to shear on x, and this is going to be, okay, okay, this is again 3.82 negative times 10 to the 6th Pascal. Well, this is 0, and this is 1, is 15.32 times 10 to the 6th Pascal, and solving for that, we get 3.6 and 93.6, okay, degrees, because they're 90 degrees apart, okay, and this is actually 45 degrees from from the principal stresses, okay. Right, so this is our, these are the values for your shear stresses, and then the principal stresses. In the next lecture, okay, the discussion of the Mohr circle will be continued. Thank you for listening, and I'll see you by then.